Okay, so far we learned about the self-supervised learning. So previously we learned about the BERT things. So using this kind of large transformer model and giving this kind of two tasks as the self-supervision, we could train the large language model and can use that for the downstream language tasks. Okay, so we used this predicting these masks and also predicting the two sentences sequence or not. This is two supervision for training this BERT. And also in the image domain, we can see this kind of self-supervised signals. So encoding the spatial relationship between two patches as the kind of, we can formulate it as the classification task. We can train the somehow the deep learning architecture. And also compared to this kind of patch spatial location encoding, this kind of jigsaw puzzling can better encode the spatial information, so we can get better self-supervisionary signals. Okay, and this is the method for that. So I mean, if we use all the combinations of the jigsaw puzzling, then that could be this number of cases. So it's too large space. So here they only use 100 cases among all the possible cases and formulated as the classification task. So yeah, that's happened in this paper. And also compared to this jigsaw puzzling, this rotation net that predicts the rotation angles of the rotated image provides better supervisionary signals. So anyways, there are multiple self-supervision methods proposed in the image domain. And also for the video, we can also can use the self-supervision, also find some self-supervision signals inherent in the video. So, I mean, for this, we can close the patches in the same video, and we can somehow widen the feature distance between the patches inside the patches which are not belonging to the same video. Okay, so this kind of using this kind of information, we can use it as the self-supervision signal. Okay, and can learn the deep learning models. Okay, and this is another method that can exploit the kind of temporal order inherent in the video. So this is the video in the correct temporal order, but we can, on purpose, shuffle the temporal orders of the video and can input it into the video encoder and then classify to find which one is in the incorrect temporal order. Okay, so using in this signal, we don't use any supervisions which have to be manually labeled, but rather than that, we can on purpose shuffle the temporal order and use it as the self-supervisionary signal. Okay. And this is a new paper published in NIPS 18. And this is for predicting some landmarks of the human body or face or any other objects. So there are two streams. This is the first and this is the second stream. And so the second stream, what they are doing is they have the network that can predict the landmarks, maybe K landmarks, spatial locations. So this is the normal pose estimation network. Okay, so given the image, the output, they are finding the key landmarks, spatial locations. So the first heat map, they are predicting the first landmarks, spatial location, and maybe the second heat map, they are finding the second landmarks, spatial location, and so on. Because there are K landmarks, we may need K heat maps. So this second network is finding the landmarks, the K landmarks of the human body here. And we will use this output as the kind of latent vector for this second network. Okay, so this second network, we are expecting that this latent vector, their feature vector, are composed of the two parts. The first is kind of the maybe human information, and the second part is their pose. Okay, so we are expecting that the first part of the feature are encoding some humans information, and second part, it is encoding some pose features. So we on purpose, at the initial step, this network and also this network, both are randomly initialized. Okay, so this network cannot properly predict the human's pose, but anyways, we will replace this as the feature for this. Okay, and also this network will also generate some random feature here. Okay, and then using this decoder, we will encode encode this image, the same image here. Okay, so and also this X and X prime have to be contained the same person, but different pose. Okay, so in this situation, this yellow feature will encode the same thing for this and this image because they are capturing the same person. But this purple latent vector have to capture the pose of this person. Okay, because of that, if we replace this purple feature using this output, using this stream's output, we can generate this person's this kind of image. Okay, so the same person as X image, but having the pose of this person. Okay, so if we train this way without any explicit the landmark position ground truth, somehow this network, both network, are becoming to work. Okay, the only supervision signals are the paired images here. Okay, a paired image having the same person but having the different pose. Okay, so by using this paired image as the supervisionary signal, we can train the pose estimation network without any pose ground truth. Okay, so using these paired images, we can train the human body landmarks estimator and also can estimate some other similar landmark estimator without giving any ground truth landmarks. Okay, so and this paper is also similar to previous. Okay, so if we are given multiple images, sorry, if we are given multiple images of the same person, but having the different view, so this is capturing the same person's image from the from the multiple views. Then what we can do is we can train this kind of autoencoder by inputting the first image and enforcing this network to generate some the same person's other view images. And in the middle, we can also giving the camera motion information to the autoencoder. So this is the conventional autoencoder, but differently to the conventional autoencoder, in the middle, we somehow can give some camera transformation metrics. Then using the multi-viewed images as the supervisionary signal, we can train the latent vectors. Okay. And the next thing we can do is using this pre-trained encoder, they may extract some useful feature for encoding the human body. Okay, and we can freeze this part and train only the shallow neural network to output the human body pose. Okay, so I mean, their concept is in the unsupervised way by providing large-scale images, they can pre-train the encoder with the rich information and then only further train the shallow networks to fine-tune the unsupervised trained network to the downstream tasks. Okay, so this is their concept in here. Okay. So are you guys following this? Okay, not very difficult. Okay, and the other useful, the self-supervised learning technique is the contrastive learning. Okay, so this is the original image. The X is denoting the original image, and this is meaning we will somehow transform the original image X. Okay, so this is the transformed images, and the F and G are, F is encoder and G is the classifier. So, and what they are doing is Because xj and xi, they are from the same original image x, they are somehow expecting that this gi and gj, their output have to be same, okay? So even though we apply some different augmentation on the original image x, they are expecting that their output, their final output, have to be same. Okay, so this is somehow the loss function that closes the activation of this gi and gj. Okay. So this is the original image, and this is the transformation they are applying to the original image to generate some xi and xj. Okay, so even though they are cropped or blurred or cut out or rotated, this have to be same in the context of the image classification. So they are, even though the images are rotated, they are containing the dog. Okay, so using this kind of signal, they are maximizing the final output, okay, their agreement, okay, and using this technique, this original contrastive learning is called as the SIM-CLR, okay, and they are somehow similar to or even better than the supervised learning techniques in multiple image classification benchmarks. Okay, so normally when we use the self-supervised learning, we think it is becoming not very competitive compared to the supervised learning. But in this task, using the contrastive learning, it is becoming even better than the supervised learning task. Okay. So nowadays, I think, yeah, many people are using these contrastive learning techniques. Okay. So this is the self-supervision things. Okay. So, and next thing is the weekly supervised learning. So self-supervised learning, it means we will not use any supervision, okay, which is manually obtained. But in the weekly supervised learning concept, it is meaning that we will use some weaker supervision, which is incomplete compared to the full supervision. Okay, so for example, when achieving this segmentation task, if we use only the image level label, which is originally obtained for image classification, or if we use the bounding box information, which is more coarse than the pixel level labels, then this is called as the weak supervised learning. Okay, so I mean the target task compared to the target task, the training data is having coarse. If the training data is having coarse-grained labels, then it is called as weak supervision. Okay. Okay. So and this is the concept of the weak supervised learning. So and maybe I will show you this for object detection task. Okay. In the context of the object detection, the weak supervisory signal might be the image level labels. Okay. The object detection, it may require the bounding box ground truth. Okay. So for an image, we have to get some bounding box information as the ground truth. But if we use only the image level label, then this situation is called as the weak supervised learning. Okay, and there would be two networks, the target network, which can perform the object detection. Okay. So this target network will generate some bounding box from given input image, okay? But we don't have any bounding box ground truth, so we cannot directly supervise this output. So we may need another network which is differentiable, and this network will somehow change this bounding box information to image label information, and then we will use the image level supervision to supervise this signal. Okay, that is concept of weekly supervised learning. So we don't have a full supervisory signal for training the target network. So we connect some intermediate differentiable layers before applying the our label, our weak label, okay? And then by getting the output from this intermediate differentiable layer, we can supervise, we can apply weak supervised signal, okay, to train both this layer and the target network. Okay, so I will explain this paper, which is introduced in CVPR 16. So this is the original object detection network, which is similar to faster RCNN, but this is called as SPP, which is similar to faster network, faster CNN, faster RCNN. And because this network's output is the bounding box information and also the classification label for the bounding boxes, but because we don't have full supervision for this classification label and bounding box information, but rather the supervisionary signal we have is the image labels only. Okay, so we have to use these differentiable intermediate layers after the output to transform the output of the object detection network to this weak supervisionary signal. Okay. So the way is like this. So here, this is some added differentiable layers. Okay, so this is the target network. This is the additional differentiable layers. So here, their output is bounding box and the classification label, but we cannot directly supervise this output because we don't have full supervisionary signal, but we have only image level signal. Okay. So next thing they did is at the end of this network, what they have is this kind of information. So for R number of regions, this is indicating the number of bounding boxes, and this is indicating the C number of labels. So in the last layers of the object detector, we will have this kind of information. So there will be R number of bounding boxes. And here, for each bounding boxes, we will have C number of label information. Okay, so for example, in the first row, it is including the class probability for the first bounding box, and the second row, it is encoding the second bounding box's probability for C number of labels. And so this is the output from the object detector. And what they do is next is they find this kind of two another tables. So the first table would be the new same dimensional table, but normalized in this direction, okay? So this is the probability. I mean, this is transforming the original this table by normalizing each columns, okay? So it is encoding for each class, which bounding boxes are most probable bounding box, okay? So this is obtained in this probability. And the other direction, these probabilities are obtained from the original table, but having the same dimensional table, but they are normalized in this direction, okay? So somehow they are encoding for each bounding boxes, they are encoding the probability for each class labels, okay? So the second output, it is encoding this table. And then what they do next is they are element-wisely multiply these two tables, okay? And then they sum in the regional direction, okay? So they element-wise multiply these two normalized tables and then sum over regions. Then here what they obtain is only the C-dimensional probability. So this is actually the image level probability for each class C, okay? So are you guys understanding this? So after summing over these regions, we can get only C-dimensional vector, which is encoding, because there are only C number of objects we are assuming to be in the image. So this is somehow becoming the image level probability now. So we can compare this output with the image level one-hot encoded ground truth, okay? So via these intermediate differentiable layers, we can transform the original output having the R by C dimensional array into this C dimensional image level supervision, and then compare this C dimensional probability with the one-hot encoded ground truth. Okay, so using the image level supervision, we can train both this and these two networks. Okay, so we can now be using the weak supervisionary signal, we can train the object detector. So this is the result. Okay, and another example is here, weakly supervised segmentation, which is introduced in ICML 18. And what they want to achieve is they want to somehow classify this image. So this is some image captured for some tissue in our body, and they are wanting to recognize if the tissue is having some disease or not. And also, they want to highlight some of the important tissues, okay, like this. So this is the ground truth patches. And somehow this is the predicted patches, okay? So they want to first classify the image itself, okay? And then at the same time, they want to detect some patches which is relevant to the, disease, okay? So this is the two tasks somehow, but we are given only the image level supervisionary signal when achieving this task. So we only have the labels that indicates this image is having disease or not. But using only that label, we want to somehow also detect the patches with that we have the relationship with that disease. Okay, and this is the ground truth, but we will not use, actually, we will not use this ground truth. We will only use this for evaluating these intermediate patches, okay? So in that sense, this could be somehow the weakly supervised segmentation task in the context of finding these patches. Okay? So we are given only image level supervision, but want to find the related patches. And what they did is they first extract some dense patches, okay, from this image, okay. So they somehow first extract some dense patches from this image, and this HK, they extract some K number of patches, okay, from this image, and then they apply the some deep learning layers to extract the hidden representation for that patch. Okay, so that's denoted as H of K, and also they apply some another deep learning layers to extract some weight for this patch. Okay, and this is one scalar value, and this H of K, that's the vector, but A of K, that's the one-dimensional scalar value. Okay. Anyways, this is vector and this is scalar, and we will sum over these K patches, okay, to get another hidden layer Z, okay. So this hidden layer Z is one vector which represents the features for whole image, okay. First, we extracted K patches from the image, okay, and for each patch, we extract H of K, which is the feature for each patch, and also we extract A of K, which is the weight for each patch, and then by summing these two, we get Z, and this G is summing over all the patches, okay? And that is actually representing the images feature now. And we will map this G to maybe connecting another MLP layer. We will compare this to some image label, okay? So this is the pipeline. So for each patch, we extract the features for each patch and also the weight for each patch. And by summing over them, we can get image level feature. And by ground truth, image level ground truth, okay? By doing this, we can train both the network that extract features for each patch and also the weight for each patch, okay? So by doing that, this is the visualization for patches weight, which is the A of K, okay? And A of K is now including how much each patch is related to this image label. Okay, some patches which have the high contributions might be have the high A of K value, and some patches which have low A of K may not contribute high for the image labels. Okay, so somehow we can at the same time classify the image level labels and at the same time classify the patches by their contributions for the whole image feature. Okay, so this is an example for the weakly supervised segmentation. Are you understanding this? Okay. Is it a bit fast or not? Understand? 다 이해되나요? 너무 빠르게 하는 것 같기도 하고 마지막이라서 사실은 네, 알겠습니다. 네. Next is the CAM, the class activation map, and this is also somehow old papers result, but I mean until now this CAM is frequently used. Okay, so somehow this CAM is derived for the image classification task. So originally, people want to classify the images, okay, verifying their main object. But when the networks are trained for image classifier, their intermediate layers may have some information for the maybe object location. So what they do in CAM is they train the deep learning network for image classification task, but they see the intermediate layers responses and verify that in the intermediate layers, they are capturing some object spatial locations. So that's the CAM approach. So this is the network which is trained for image classifier. Okay. So at the last layer, it is outputting the probability for some K object. Okay. So by inputting this image, they are outputting some object probability. Okay. And last layer, they are constituting the last layers of this network like this. So this is the intermediate feature map, okay, here. On purpose, they are having the two-dimensional feature map, okay? And we'll call it as FK. And this K is the, there could be K intermediate feature map, okay? And also we can multiply some weight at the last layer. We can multiply some weight to this 2D feature map. Before that, we will apply some pooling, average pooling to make this each feature map to one-dimensional scalar value. And then, so this is indicating that average pooling. So this is the 2D feature map, but we will average this XY coordinate to make it into the one scalar value. And by applying this weight, additional weight, we will make the probability vector. Okay, that is the original way to train the image classifier. But without applying the pooling, so originally there was the pooling layers here, but by removing the pooling layer and directly multiply this weight, this is can be visualized like this. So this is Fk x comma y, maybe F1. This would be F2 x comma y. This is Fn x comma y. Okay, so we can multiply each weight and then summing to obtain this kind of MC. Okay, so the original networks are trained for the image classifier, But by obtaining the intermediate responses and by extracting the intermediate 2D responses, like here, and by multiplying some predefined weight for that intermediate features, and by adding them, we can get this kind of activation map. And they are somehow capturing the class locations. Okay, so this is the CAM method. And this can be somehow used for weakly supervised detection or segmentation tasks. So previously, these networks are trained for image classification task using only image level supervisions, but they are somehow capturing the object locations, okay? And now they can be transferred to object detection or segmentation task. In that sense, they can be frequently used for weakly supervised detection or segmentation tasks. And somehow, CAM is used to obtain the fine segmentation masks. So this is some previous method that can remove some noises. So this is the unary classifier, which is obtained for each pixel. So if we classify each pixels of these images, then that could be very noise, okay? So this green color is denoting that these regions are classified as the tree, and this gray is indicating that these parts are classified as sky, and so on. And green is denoting they are chair, and so on. But this unary is meaning that each pixel was classified independently without considering each other. But this CRF methods are somehow considering the nearest pixels. Okay, so there are some prior that each pixel nearby need to have some similar object. Okay, so this is the result by getting some pixel-wise independent pixel-wise classifier. But after considering the nearby priors, the result could be better than previous. And this is considering the more dense priors. So nearby, so how much nearby pixels we see could be depending on some complexity. So if we see only 8 pixels nearby to this center pixel, then the time complexity could be less, but the precision, the accuracy could be limited. But this fully connected CRF means they will see all the relationship between these pixels, okay? So for this center pixel, they will consider all the relationship between this, this pixel and whole pixels in the image. They will see the relationship. And actually this paper can achieve it by approximating their prior, okay? So given this unary result, they can refine the original noises like this. And this is ground truth, and they are quite similar. Okay. So this is the more specifics for this paper, but I think we don't need this maybe. But anyways, using these techniques, we can refine the original CAN algorithms. This kind of cores result we can get, but using this kind of technique, we can refine this to make it like this, okay? But CAM is having some limitation that it only captures the most discriminative part of an object, okay? So for example, here, when we apply CAM, then it only activated to most discrete part of the object, okay? So here, it only activated to here, right? Okay, because that are most discriminative information, okay? But so sometimes when using CAM, the bounding box is also shrinked to this only most discriminative part, okay? So this bounding box is not capturing whole gun like this, but only capturing this most discriminative part. So in this paper, they are on purpose using the thresholding and making some mask and dropping on purpose, they are wanting to remove most discriminative part and randomly having this mechanism during the training to make the CAM attend to some less discriminative part. Okay, so this is some interesting idea, so I attach it here. So using their method, their activations are more extended compared to the original CAM. So here they are capturing whole object, okay, rather than the most discriminative part. Okay. Anyways, this is some technique that can be used for weekly supervised learning things. Okay, and then let's move to the next theme. So, are you guys following this? It may not be maybe very difficult in the conceptual level, okay? And the next thing, the last theme in this course is the visual language models. So nowadays, as you know, language models are very popular, right? You may heard about the ChatGPT, okay? So, but this is the language model which was originally driven for the natural language processing task. But nowadays, the VLMs are becoming popular, okay? So even in ChatGPT, we can input both the images and text, okay? So previously only text we can input to the ChatGPT, but nowadays we can also input the images to the ChatGPT. So most of the vision tasks are also becoming to use these visual language models. So the last lecture is covering that. Okay, so maybe before explaining the visual language models, I may have to introduce some language models first. And this is the GPT-1, and they were introduced by the OpenAI by this Archive 18 paper, okay? So they are using the transformer architecture like this, okay? And using this kind of self-supervisionary signal, seeing only the previous word, they predict the next word, okay? This could be achieved in the self-supervisionary way, okay? So they first pre-train their transformer using unlabeled data in the self-supervised way, and then they fine-tune their network to some downstream tasks which have ground truth Y, okay? This is the concept used by the GPT-1. And this is the multiple downstream tasks. And they are saying that they could obtain better performance compared to the LSTM when using the transformer. And also, without using pre-training, they can get the better performance. Okay, that's the two things we have to learn here. So they are somehow proving that if they are given many unsupervised data, and if they train their network using that many unsupervised data in the self-supervised way, then they can get better performance in the downstream tasks. And this is the BERT, which is similar to GPT-1, but I mean, this is also doing the similar task, and this is actually we saw last lecture. And they also use some unsupervised signal to train the transformer, and then apply this to large, many downstream tasks. Okay. Okay. So, and they are saying they get better performance than GPT-1, and this is mostly because they are using the larger scale architectures compared to the GPT-1. And this is the this is the also the GPT-3. So GPT-1 is provided in 2018, and the GPT-3 it appears in 2020. And BERT is 2019. Okay, BERT have the larger parameters than this is 2020, larger parameters than GPT-1, and also this GPT-3 it has larger parameters compared to GPT-1, BERT, and GPT-2. Okay. Okay, this is some other variant in GPT-3 models. Okay, and this is the GPT-3, and this is BERT, and this is GPT-1. Okay, they are having larger parameters, and they are saying if they have large language models, then it can also generalize, have the good performance in also the future learning. Okay, so this is the accuracy, and this is the training data size. Okay, so I mean, if they have more parameters, the ability to generalize also becomes exponentially. Okay, that's the the paper title is also having that signals. So language models are now future learners. So now, if they pre-train large-scale transformer with the large-scale data in the unsupervised way, they can be future learners. Okay. And this is the data set they have used. So they use a billion-scale data. Okay. And so they show that their performance is better than previous. Okay, and now we have GPT-4 and also having the ChatGPT. Okay. Yeah, and maybe I have to maybe deal with this clip maybe and finish this class. Okay. So this clip is maybe also this is also introduced by OpenAI. Okay, and also introducing this ICML 21 paper. And there have been multiple algorithms that try to align between the image, the vision signal, which is image and text. Okay, so there have been some algorithms that try to align this image and text, but this clip is most popular algorithms among them. So they do contrastive pre-training, and so this is their testing pace. So this is the training, and this is the testing part, okay? So in their training, they have to involve two networks, okay? First is the text encoder that encode this kind of text signal. And the second network is the image encoder that encode this type of images, okay? So they need these two networks, and both are trained during the training stage, okay? And so maybe there during the training, we are using N batches. So we have N text and N images, okay? So we extract first N text, okay? N text features we first extract, and also we extract N image features here, okay? And then this might be the ground truth, okay? Okay, so I1 will have the correct text feature T1, and I2 will have the correct text description T2, okay? So these diagonals are indicating the ground truth mapping between image and text, okay? But the remaining, their entries are having some false matching, okay? Maybe there could be some true matching accidentally, but we are regarding this is false, and only these diagonals having the true matching, okay? So we are wanting to increase this diagonal. So I mean, what they do here is they are dot producting between this I1 and T1, their vectors. If we do dot producting, then if the two vectors are similar, they will have the value close to 1. If they are different, then they may have a value close to 0, okay? So in here, they are having the dot producting between these two vectors. So we are wanting to increase the diagonal indexes, but try to minimize these remaining cells, okay? So in that context, they are called as the contrastive pre-training, okay? Using text and image pairs, we can train the image encoder, and text encoder by using this kind of losses, okay? This is the contrastive pre-training. And in the testing, what we can do is we can actually achieve this kind of zero-shot prediction. So when we input this image, we can use image encoder to get their feature I, okay? And also, we can use this trained text encoder to input some text, okay, here, okay? And then by comparing text feature and image feature, we can select one best matching that best describes the image feature, okay? So by this manner, we can classify the images, okay? I mean, this is somehow different process to the conventional image classification. So, I mean, in the conventional image classification network, in the last part, there have to be k-dimensional vector that indicates the probability for k predefined object, okay? So we cannot classify images outside of these k objects. But here, the thing is, we can freely augment these text vectors by inputting more text we want to, okay? So, and if that new text is having the higher probability than other text description, then that would be selected as the best description for that image. Okay, so in that sense, this clip can be used for the zero shot prediction. Okay, so detecting the best description that describes these images properly. Okay, so that's the merit of this clip. Okay, so this is the thing for the training. Okay, and yeah, they are trained using many text and image pairs. Okay, and using the transform architecture for both image and text encoder they use. Okay, and for other characteristics, we will review that from the next class. Okay. Okay. Thank you. And we will see this from the next class. Okay. Thank you.